Dear PLIA committee, ladies and gentlemen, my name is Chryso and I'm a PhD candidate in the Department of Architecture in the University of Cyprus. The concept presented herein is part of the ongoing research program HyBuild, which is funded by the European Union through Horizon 2020 and has the title Evaluation of Thermal Comfort and Energy Performance of a Case Study in Vernacular Architecture of Cyprus. Special acknowledgement to Michail Haralambous and Efthymiou for their feedback on this paper. Vernacular architecture incorporates passive bioclimatic design features that can be used as lesson for the contemporary architecture, and therefore it is important to preserve its value. The vernacular architecture of Cyprus can be characterized as an excellent example of bioclimatic architecture. This study focuses on the environmental assessment of these spaces through the monitoring of indoor conditions of the traditional building. In the framework of the research program HyBuild, a traditional building was selected to be an example where a hybrid electrical thermal storage system will be installed in the Mediterranean region. The selection aims at the rehabilitation of vernacular buildings and the promotion of both bioclimatic features incorporating vernacular architecture and new technologies that can be adapted in such buildings. So, this is a vernacular building under study located in Aglanja area in Cyprus. Like the rest of the island, Aglanja has a Mediterranean climate with hot dry summer and relatively cold wet winter. With regards to typology, the building plan is I-shaped as a more compact and simple form of linear placement of the individual spaces. The traditional buildings are characterized by main spaces with high ceiling of approximately 4.5 meters. The building under study has a 50 cm thick stone masonry wall. The roof is slightly inclined and during the retrofitting period, extruded polystyrene of 12 cm thickness has been added, improving its energy performance. The windows consist of single glazing with 30% of surface to be wooden frame. For the investigation of the thermal performance of the vernacular building, a field study has been carried out from January 2019 and is still in progress, covering all seasons. Specifically, air temperature and relative humidity were measured using the HOPO data logger and mean radiant temperature, globe temperature, and air velocity using LASTEM base module. All parameters were logged at 1.1 meters height from the floor as per the European standard. Additional data loggers were placed in one selected position along different heights of the room, that is 1.1 meter, 1.7 meter, 2.3 and 2.9 meter in order to examine the contribution of temperature along the height. These are some photos from the installation and equipment. The objective was to evaluate the thermal comfort condition of traditional buildings. Thermal comfort is assessed using the Adaptive Comfort Standard, which is incorporated in ASHRAE 55, and degree hours was used as an indicator of the energy performance. This figure shows the indoor temperature evolution in the different rooms of the building and outdoor temperature throughout the year. But let's see in greater detail the graph. During winter period, the mean average temperature in all spaces are found to be low but stable, and all rooms show similar behavior in terms of temperature. Nevertheless, it is interesting to mention that during winter period, the building shows much higher temperature compared to the outdoor conditions. Specifically, the mean average indoor temperature in the building was around 12 degrees Celsius compared to 0 of the outside. During the summer period, indoor maximum temperatures are of about 10 degrees Celsius below maximum outdoor temperatures and show very small diurnal fluctuation of about 1 degree Celsius during the day. However, due to this low fluctuation, the indoor average temperature is always higher than the corresponding outdoor one and was about 28 degrees Celsius. The results of different data loggers along different heights of the rooms show that during the winter period the difference is negligible. However, during the summer period the difference was about 0.5 degrees Celsius from 1.1 to 2.9 meters. Taking into account that the building has a mean height of 4.5 meters, the difference is expected to be much higher at the top. This shows the positive contribution of high ceilings, keeping indoor spaces cooler during the summer. This is the Bragg index of operative temperature of the building from January to December, which shows the percentage of data within the comfort zone. Actually, the results show that between January and March, the building failed to maintain thermal comfort as no recorded time fell within the acceptability limits and required a large amount of energy to keep indoor thermal comfort. During the late intermediate period and early summer period, the building provided acceptable indoor temperatures without the aid of artificial systems. However, the building required much less energy for cooling. The recorded data for relative humidity show that for most of the time the building totally meets the norms, with values between 40 to 70%. During February and March, the building exhibits higher relative humidity due to lower indoor temperature, having only 20% of the data between acceptability limits. For the improvement of thermal comfort and energy performance, passive measures should be considered during the normal operation of the building. Based on the bioclimatic chart during the heating period, passive solar system and internal gains are required. During the intermediate period, the temperatures are mild and overlaps the comfort zone for the largest parts of the day. During the cooling period, a number of cooling strategies are proposed, such as ventilation, night ventilation, and evaporate cooling. So, to conclude, vernacular buildings perform very well during the intermediate and summer period, keeping within the comfort zone most of the time. During the winter period, the building requires additional heat gains to maintain indoor thermal comfort and acceptable relative humidity levels. The indoor temperature of vernacular buildings is very stable and with very low fluctuation throughout the day. This study provides a basis for the formulation of a site-specific design strategy to improve thermal conditions and achieve energy conservation within lowland vernacular construction in diverse climatic conditions. This is the consortium. Thank you for your attention.